On September 24th, 2020, a team of climate scientists published something they had not set out to find. They had drilled deep into a glacier high in the Alps, a place called Colle Gnifetti, to read the planet's old weather the way you might read the rings of a tree. In the layers laid down from 1914 through 1919, the ice held a clear and unusual signal. For 6 straight years, cold, salty air off the North Atlantic poured over Europe and would not leave. It was the strongest pattern of its kind in 100 years. If you like a calm, careful look at how the Earth works, you're welcome to subscribe, and we will keep these reports coming. Those same 6 years frame 2 of the worst things people have ever lived through. The First World War killed about 20 million. The influenza that followed killed at least 50 million, more than any single outbreak on record. This report walks through what that stuck pattern was, how the ice remembered it, why it likely deepened both disasters, and what it does and does not tell us about the sky above us now. High on the border between Switzerland and Italy, there is a saddle of old ice called Colle Gnifetti. It sits nearly 15,000 feet up, in the thin cold air where the snow that falls in winter does not all melt away in summer. Some of it stays. The next year's snow presses down on it, and the year after that presses harder, until the buried snow turns to ice. Layer rests on layer, oldest at the bottom, like pages in a book no one wrote on purpose. A team of climate scientists went up there and drilled straight down through those pages, pulling out a long cylinder of ice that reached back more than 100 years. When they read it, one stretch stopped them. The ice laid down between 1914 and 1919 carried far more sea salt than the years on either side. Sodium and chloride, the 2 parts of ordinary salt, sat thick in those layers. Salt that high in the mountains does not come from the ground. It comes from the ocean, lifted off the surface of the North Atlantic by wind and carried inland on the air. A little of it always reaches the Alps. This was not a little. For 6 years running, the salt stayed high, and the researchers found nothing else like it across the whole century the core covered. They called it a once-in-a-100-year event, and the wording was careful, because the ice gave them the evidence to say it. That is why this small column of frozen water matters. It is a record of the air itself, of which way the wind blew and what it carried, written down at the time and kept frozen ever since. We have weather diaries from those years, and battlefield reports, and tallies of the dead. What we did not have, until this core came out of the mountain, was a clean physical measurement of the sky over Europe during the worst 6 years that continent had known in living memory. The ice gave us that. It did not depend on anyone's memory or anyone's record keeping. It simply held what the wind delivered. The 6 years are the reason the team kept pulling at the thread. 1914 is when the First World War began. 1918 is when the influenza pandemic tore through a world already worn down by that war. By 1919, both were ending. The ice was telling them that across the exact span of those 2 disasters, the air over Europe had behaved in a way it had not behaved before or since, at least not this strongly. The salt was the first clue. It said the ocean was reaching much farther inland than usual, again and again, for years. A signal like that invites a plain question. Salt in the ice means ocean air over the land, but it does not by itself say cold or wet or deadly. To get from a chemical trace to a story about weather, the team had to ask what kind of pattern pushes that much sea air over a continent and holds it there. They had to look at temperature and rainfall, at where the storms tracked, at the great pressure systems that sit over the Atlantic and decide, season by season, whether Europe gets mild air from the south or raw air from the north. The salt pointed them toward the north and toward a machine in the atmosphere that, in normal years, keeps swinging back and forth and rarely gets stuck. It is worth sitting with how strange it is that we can know any of this. A war that ended more than a century ago, a flu that burned out long before anyone alive today drew breath, and yet the conditions of the sky in those years are still there to be measured, locked in a glacier that has been quietly keeping the receipt the whole time. The scientists did not have to guess at the weather. They could weigh it. Before we follow the salt north to the storm track, it helps to understand the trick at the heart of all this, the reason a frozen core can speak about wind and ocean at all. The ice does not just trap water, it traps dust, ash, acid, and salt, each one a kind of message about the air it fell through. Read the right way, a glacier becomes an instrument. So the next thing to understand is simple and a little surprising. A block of mountain ice can smell the sea. Snow is not clean. It looks clean, but every flake forms around a speck of something, and on the way down it sweeps up more. Dust off a far desert, ash from a fire, acid from a volcano, and tiny grains of salt lifted off the ocean all ride down with the snow and land on the glacier. When that snow turns to ice, those specks are sealed inside, sorted by the year they arrived. So when the team melted small slices of the Colle Gnifetti core and ran the water through their instruments, they were not really measuring ice. They were measuring everything the ice had caught. The salt is the part that matters here. Out over the North Atlantic, wind tears across the wavetops and flings up a fine spray. The water in that spray evaporates and leaves behind microscopic flecks of sea salt, light enough to float on the air for days and travel hundreds of miles. Most of it falls back into the sea or drops over the coast. A small share rides the wind inland and higher up, and a smaller share still reaches a glacier in the Alps and settles into the snow. The more ocean air that pushes over the land and the stormier that air is, the more salt arrives. Count the salt and you are really counting how hard and how often the sea breathed on the continent. This is why the 6-year stretch stood out so plainly. The sodium and chloride in those layers told the team that marine air had been flooding over Europe far more than usual, season after season, without the long calm breaks that normally come between. The ocean was not reaching the Alps in occasional gusts. It was leaning on the whole continent. To trust that reading, the scientists had to be sure they knew which layer belonged to which year. That is the hard part of ice core work, and it is worth being honest about. Near the top of a glacier, the yearly layers are thick and easy to separate, because the weight above has not squeezed them much. Deeper down, the same year's snow gets pressed thinner and thinner until counting becomes delicate. In this part of the core, the team worked with a possible error of about a year either way. That sounds loose, but for a 6-year event it is tight enough. A signal that lasts that long does not hide inside a 1-year wobble. The shape of it holds. They did not rely on the ice alone, and that restraint is part of why the result is convincing. A single record, however clean, can mislead. So they lined the salt up against other things people had written down at the time. They checked it against measured temperatures from across Europe, against rainfall records, against the count of deaths in country after country. If the ice was right about the air, those independent records should agree, and they did. The years the salt ran high were also the years the thermometers ran cold, and the rain gauges overflowed. Several different kinds of evidence, gathered by different people for different reasons, all pointed the same way. There is a comparison worth making just once, because the idea of reading air from ice can feel like a stretch. Think of a smell that gets into a house. If a kitchen burns something, the smell soaks into the curtains, and a visitor the next day can tell what happened without being told. The glacier works a little like that. It cannot help absorbing what passes over it, and a careful reader can come along long after and reconstruct the event from what stuck. One of the researchers put it almost exactly that way. The glacier, he said, smells the air the same way your nose does. So the core had given them a measurement they could defend. The air over Europe carried an unusual load of ocean salt for 6 straight years, the coldest and wettest the records show, stronger than anything in a century. The measurement was solid. The meaning was not yet clear. Salt over the land is a symptom, not a cause. Something had to be steering all that sea air inland and holding it there, year after year, against the normal rhythm of the seasons. To find it, the team had to look out over the Atlantic itself, at the 2 great weather makers that decide what kind of air Europe gets. That is where we go next. Out over the North Atlantic sit 2 enormous, mostly invisible features that shape the weather for hundreds of millions of people. One is a region of low air pressure that usually parks near Iceland. The other is a region of high air pressure that usually sits farther south, near the Azores Islands off Portugal. Neither is a storm you could photograph. Each is a broad, slow, standing pattern in the atmosphere, the kind of thing you only see on a pressure map. Together they run a kind of engine, and the air over Europe is what that engine moves. The way it works is simpler than it sounds. Air flows from high pressure toward low pressure, the same way water runs downhill. With high pressure near the Azores and low pressure near Iceland, the air between them gets pushed along, and, because the planet is spinning, it bends into a steady west to east flow. That flow is the band of westerly winds that carries weather systems across the Atlantic and onto Europe. When the two pressure centres are both strong, the engine runs fast. The westerlies come in straight and brisk, sweeping mild, moist ocean air over Britain, France and the lands beyond, keeping winters comparatively soft and wet and summers steady. Scientists track the strength of this engine with a single measure called the North Atlantic Oscillation. The name is a mouthful, so hold on to the plain version. It is just the difference in pressure between the Iceland area and the Azores area, and it tells you how hard the air is being pushed across the ocean toward Europe. When the gap is wide, with a deep low and a strong high, the index is in what they call its positive phase, and the westerlies are powerful. When the gap narrows, with a weak low and a weak high, the index turns negative, the steady west to east flow loosens, and the door opens for other kinds of air to come in from odd directions, often cold air spilling down from the Arctic. What makes the system interesting, and what makes it hard, is that it is restless. The two pressure centres do not hold still. The Iceland low in particular drifts. In some years it sits where the textbooks put it, west of Iceland, and the winds behave. In other years it slides east of Iceland and changes everything downstream, steering raw northern air into Europe instead of mild Atlantic air. The whole arrangement swings back and forth on its own, week to week and year to year, and most of the time it does not get stuck in any one mode for long. That restlessness is normal and healthy. It is why a cold snap usually gives way to a thaw, and a wet spell to a dry one. There is a nice back and forth built into a normal year. For a stretch, Europe might draw cold winds curling down from around Iceland. Then the pattern shifts, and the continent gets warm, dry air riding up from the south, the kind that sometimes carries a faint red dust all the way from the Sahara, and drops it on cars and rooftops in Italy and France. Cold from the north, warmth from the south, trading places through the seasons. The engine breathes in and out. No single mood lasts. This is the machinery that the salt in the ice was pointing at. Sea salt that high over the Alps means a lot of ocean air pushing inland, and the amount and direction of that push are set by exactly these two pressure systems and the winds between them. So once the team saw 6 years of heavy salt, they knew the question was not really about the Alps at all. It was about the Atlantic. Something must have happened to the Iceland low and the Azores high, or to the dance between them, to send that much marine air over the continent for that long. The healthy version of this system swings and resets. The dangerous version does not. The single most important thing to understand about what the ice recorded is that, for 6 years, the engine appears to have lost its swing. The normal back and forth slowed almost to a stop, and one mood settled in and stayed. To see why that matters so much and why those particular winters left such a deep mark, we need to look at what happens when this great Atlantic engine jams. A weather pattern that comes and goes is one thing. A weather pattern that arrives and refuses to leave is another thing entirely, and it is the second kind that the ice core points to. The salt did not spike for a single hard winter and then settle. It stayed high across 6 years. For that to happen, the Atlantic engine could not have been doing its usual restless swinging. It had to have locked into one position and held there far longer than it should. The position it locked into was the cold, wet one. In the team's reading, the Iceland low became unusually dominant and lingered over Europe, while the normal rhythm that would have broken its grip failed to kick in. With the low sitting where it did and staying put, the continent kept getting fed raw, moist ocean air from the north and northwest over and over through season after season. The system that should have swung the continent back toward milder spells simply did not swing. One scientist on the team described it plainly, saying the atmospheric circulation changed and brought much more rain and much colder weather all over Europe for 6 years. 3 winters stand out inside that long stretch, and they line up with the worst of the salt and the worst of the deaths. The winters of 1915, 1916 and 1918 each brought an especially strong surge of cold ocean air across Europe. These were not gentle dips. They were sharp influxes of frigid wet air. The engine jammed hard into its coldest setting, and the ice recorded each one. Those same 3 winters, as we will see, show up again in the record of how many people were dying. The timing is the heart of the whole study. It helps to picture why a stuck pattern hurts more than a passing one. A single cold, wet month is hard, but the ground dries afterward, rivers fall back, and people recover. When the same pattern holds for years, nothing gets the chance to reset. The soil never fully drains. Each new storm lands on ground already soaked from the last. Cold that would be bearable in a normal winter becomes punishing when there is no warm spell to recover in. The damage does not just add up, it compounds, because the system never returns to baseline between blows. This is the difference between a setback and a siege. A setback passes. A siege wears you down by never lifting. For 6 years, by the Ice Core's account, Europe was under the weather equivalent of a siege, with the relief that normally comes after a bad stretch arriving late, or weakly, or not at all. And this was happening to a continent that was, at the very same time, tearing itself apart in the largest war it had ever fought. It is worth being careful here about what the ice can and cannot say. The core gives a strong, well-dated signal that ocean air dominated and that the pattern persisted. It is honest evidence that the Iceland Low and the westerly system were behaving abnormally for years. What the core cannot do is reach back and explain, with certainty, every reason the pattern got stuck. Why the engine jammed when it did, and held as long as it did, is a harder question, and we'll come to the possible drivers later, marked as the open question it still is. For now, the firm part is the persistence itself. The mood lasted. That persistence is the thread that ties this whole story together. A war was being fought in the open air, in fields and trenches, by men who had to live outdoors in whatever the sky delivered. A virus was waiting in the wings, the kind that spreads best when people are crowded, cold and weakened, and the sky, for 6 straight years, delivered cold and rain, and more rain, without the breaks that normally come. The jammed engine was the stage on which both disasters played out. Once a pattern like this sets in, the most direct thing it does is open a path for northern air to pour south, unblocked, again and again. That is the next piece to understand, because it explains both the salt in the ice and the misery on the ground. With the usual barrier weakened, the door to the north stood open, and through it came the cold. When the Atlantic engine runs normally, it acts a bit like a guard at a door. The strong band of westerly winds flowing steadily from the ocean toward Europe forms a kind of moving wall that keeps the coldest Arctic air penned up to the north where it belongs. Mild, damp ocean air comes through instead, and Europe gets the grey, soft, drizzly weather it is known for. The guard is not perfect, but in a normal year it holds the line often enough that hard Arctic outbreaks stay brief. During the 6-year anomaly, that guard stepped away from the door. With the Iceland Low sitting in the wrong place and the westerly flow weakened, the moving wall lost its strength. The barrier that normally keeps northern air in check sagged, and cold air from around Iceland and the Arctic edge could spill down into Europe almost at will. Worse, because the pattern was stuck, the door did not swing shut again the way it usually would. It stayed open, and the cold kept coming. This is exactly what leaves a salt signal in an Alpine glacier. The air pouring down was not dry continental air. It was marine air, fresh off the storm-tossed North Atlantic, loaded with sea spray and moisture. As it swept over Europe and rose against the mountains, it dropped its salt and its rain. So the same open door that let the cold in also explains the chemistry in the ice. The high sodium and chloride were the fingerprints of ocean air arriving in bulk, again and again, instead of the occasional visit a normal year would bring. The researchers traced this back to the behaviour of the Iceland Low in particular. In an ordinary setup, that low-pressure centre sits out west of Iceland, and the cold winds it generates curl around in a way that does not bury the continent. During the anomaly, the pattern shifted so that the low's influence pressed harder and longer onto Europe itself. Picture a fan that normally points off to the side suddenly turning to blow straight at you, and then jamming in that position. The flow of cold, wet air that would normally graze the edge of the continent was now aimed right across it, and the switch that would turn the fan back stopped working. There is a detail here that makes the picture sharper. Europe's weather usually comes from a contest between 2 sources: the cold from the north around Iceland and the warm, dry air that rides up from the south near the Azores, sometimes carrying that faint Saharan dust. In a balanced year, these 2 trade off, and the trading is what gives the continent its variety. During the anomaly, the contest stopped being fair. The northern source dominated month after month, and the warm southern air that should have pushed back and dried things out lost the argument again and again. With one side winning for years, the weather had no reason to change its mind. For the people living under it, the open door had a brutal simplicity. Cold and wet do not need to be dramatic to be deadly over time. A man who is never able to get warm and dry, who sleeps in damp clothes night after night, whose food and shelter are always a little worse than they need to be, is a man whose body is slowly being spent. Multiply that by the millions of soldiers living outdoors along the front, and by the civilians behind the lines coping with ruined harvests and short supplies, and you have a whole continent being quietly drained of its strength, not by any single storm, but by the refusal of the weather to ever let up. This is the condition the ice core lets us measure, and it is the reason the salt and the suffering belong in the same story. The open door to the north was not a metaphor the scientists reached for. It was the physical setup that produced both the marine air in the glacier and the cold misery in the field. The two are the same event seen from two angles, one frozen in a mountain, the other written in casualty lists. What an open northern door delivers more than anything is water. Cold air off a stormy ocean is wet air, and when it keeps coming it brings rain that does not know how to stop. That endless rain is the next thread, and it is where the weather stopped being a background condition and started killing people directly. Of everything the anomaly brought, the rain may have been the worst, because rain does its damage slowly and everywhere at once. Cold you can sometimes fight with fire and shelter. Rain that falls for weeks, on ground that never dries, soaks into everything, and takes the fight out of people without ever looking like a disaster. The ice core and the old weather records agree on this point. Across those years, and especially in the cold winters, Europe was wetter than it should have been, and the wetness lasted. The reason follows directly from the open northern door. The marine air streaming over the continent was carrying ocean moisture, and as that air ran into hills and mountains and the edges of weather fronts, it wrung itself out as rain and snow. With the pattern stuck, there was no long dry interval to let the land recover. Storm followed storm. The rain gauges of the time, kept by ordinary weather observers across many countries, recorded the totals, and when the team lined those totals up against the ice, the wet years matched the salty years. Two completely different ways of measuring the same sky told the same story. Standing water is the part that turns weather into a health crisis. When fields flood and stay flooded, and when low ground becomes mud that never firms up, several bad things happen together. People are constantly wet and cold, which steadily wears down the body's defences. Clean water and dirty water mix, which spreads sickness. Food production suffers, because crops rot in the field or never get planted, and hunger weakens people further. None of this is dramatic on any single day. All of it is deadly over months and years. The researchers were careful to connect the rain to real, measurable harm rather than just describing bad weather. The cold and the rain, in their account, raised the death toll directly, before the influenza ever became the main story. People were dying of exposure, of pneumonia, and other infections that thrive in cold, wet conditions, and of the knock-on effects of ruined food and fouled water. The weather was not setting a mood. It was filling graves. It helps to remember how much of a life back then happened outdoors and unprotected. This was a time before the comforts we now take for granted in much of the world. Heating was simple and often scarce. Clothing, once wet, stayed wet. Shelter for millions of soldiers was a hole in the ground. For civilians, a bad harvest meant real hunger, not just higher prices. In that world, a sky that poured cold rain for years was not an inconvenience. It was a direct assault on the body's ability to keep itself alive, and it hit hardest exactly where people had the least protection. There is one comparison worth making, and only one, because the scale can be hard to feel. Think of how a single long, wet, cold spell can fill hospitals even today, with falls, with chest infections, with the old and frail slipping under. Now imagine that spell not lasting a week but stretching across 6 years, falling on a population already short of food, medicine and rest, much of it living in the open. The same forces that crowd a modern emergency room for a few bad days were pressing on tens of millions of people, with no relief in sight, season after season. The ice core's gift is that it lets us say all this with more than sympathy. We are not merely guessing that the weather was bad in the war years from old letters and grim photographs. We can measure that the air was abnormal, date it to within about a year, confirm it against independent temperature and rainfall records, and watch it track the rise and fall of deaths. The endless rain stops being a detail of war stories and becomes a measured force with a body count, and it is the bodies that come next. The first place this weather turned into mass death was not the hospital ward, but the battlefield, where men were already being asked to live and fight in the open. The rain that filled the fields also filled the trenches, and the front line became one of the deadliest places the anomaly touched. That is where the story goes now, into the mud of the Western Front. The Western Front ran for hundreds of miles across northern France and Belgium, a double scar of trenches where two huge armies faced each other for years. Soldiers lived in those trenches, dug into low, flat, often clay-heavy ground, with the water table never far below their boots, in a dry climate that would have been miserable. Under the 6-year anomaly, with cold marine air and relentless rain pouring over exactly this part of Europe, it became something closer to a slow drowning. The rain that the ice core recorded fell hardest on a landscape least able to shed it. Artillery had churned the fields into a moonscape and destroyed the natural drainage, so the water had nowhere to go. Trenches filled. Shell craters became ponds. The famous mud of the First World War, the mud that swallowed men and horses and equipment, was not bad luck. It was the predictable result of heavy, persistent rain landing on ground that had been blasted flat and could no longer drain. The weather and the war made the mud together. This is where the study's timeline gets its sharpest edge. The crests of the cold, wet anomaly line up with some of the war's most notorious battles. The fighting at the Somme, at Verdun, and at Gallipoli all unfolded against this backdrop of foul weather, and the historical accounts of those battles are full of it. Men did not only die from bullets and shells, they died from frostbite, from exposure, from pneumonia, and from infections that festered in the wet. Some, caught in flooded ground at the wrong moment, simply drowned in trenches and craters. The weather was a second enemy that never stopped firing. It is worth stating the mechanism plainly, because it is easy to let it hide behind the famous battle names. A soldier who is always cold and never dry is a soldier whose body is constantly spending energy just to stay alive, leaving less for healing and for fighting off infection. A small wound that would close cleanly in dry conditions can turn septic in mud. A chest that is always damp and chilled is a chest where pneumonia takes hold. The wet did not need to kill directly to be lethal. It tilted every other danger toward death. The senior historian on the team, Michael McCormick of Harvard, made the point that the ice core had handed them something they never expected. They had set out to read a century of climate, and they ended up shedding light on the weather in the trenches and on the pandemic that followed. That is an honest description of how the discovery happened. No one drilled into a glacier hoping to explain Verdun. The connection emerged because the dates lined up too well to ignore, the salt in the ice matching the misery in the records year for year. There is a human weight here that the numbers alone do not carry, and it deserves a calm word. Behind the casualty figures were individual men standing in cold water for days, unable to feel their feet, watching the rain come down on a field where the next attack would come. The anomaly did not care which side they were on. The same weather fell on every trench. Whatever the generals intended, the sky added its own toll on top, and the ice core lets us see, 100 years later, that the sky was loaded against them in a way that had not happened in a century. We should be careful not to overstate it. The First World War would have been a catastrophe under any weather. Most of the roughly 20 million who died in it were killed by the war itself, by weapons and starvation, and the collapse of order, not by rain. What the study argues, and argues with measured evidence, is that the anomaly made an already terrible situation worse, raising the toll at the margins and grinding down the survivors. That is a more honest claim than saying the weather caused the slaughter, and it is the claim the ice supports. The grinding down is the part that carries into the rest of the story. A continent of soldiers and civilians worn thin by years of cold, wet and hunger is a continent with weakened defences, primed for whatever comes next. Before the flu arrived, that wearing down was already showing up in the plainest possible measure, the number of people dying month by month. The deaths began to climb in step with the weather, and that rise is the next thing to follow. Long before the influenza became the main killer, deaths across Europe were already rising and falling in a pattern, and the pattern had a rhythm that matched the sky. When the team compared the climate record to the count of deaths across 13 European countries, they found that mortality in Europe peaked 3 times during the war years. Each of those peaks came during or soon after the strong influxes of cold, wet ocean air, the surges that hit hardest in the winters of 1915, 1916, and 1918. The weather went bad, and the dying went up, again and again, in time. That timing is the strongest evidence in the whole study, stronger even than the salt itself. A single match between bad weather and high deaths could be a coincidence. 3 matches, spaced across years, each one tied to a measured surge of cold ocean air, is a pattern. And because the death records came from many different countries, kept by many different officials for their own reasons, they form an independent check on the ice. The glacier said the air was cold and wet in those years. The civil record said people died more in those same years. Neither was built from the other. They agree because they are describing the same reality. The mechanism behind the rise in deaths is not mysterious, and it does not require the flu to explain it. Cold and wet, sustained over months, kill people in ordinary, well-understood ways. Pneumonia and bronchitis climb. The old and the very young, always the most fragile, die in greater numbers when they cannot stay warm and dry. Poor harvests in waterlogged fields mean less food, and hunger both kills directly and makes every illness more dangerous. Crowding, as people pull together for warmth and shelter, helps any contagious disease move faster. These forces were all turned up at once for years, across a whole continent. It matters that this rise began before the pandemic, because it tells us the population was being weakened in advance. By the time the influenza arrived in force, Europe was not a healthy place suddenly struck by a new disease. It was a place already worn down by years of cold, hunger, infection, and the strain of war. A place where defences were low and the most vulnerable had already been pushed to the edge. A virus landing on that kind of population finds far more dry tinder than it would in a rested, well-fed one. The study is careful about cause here, and so should we be. Weather sits among many forces shaping how many people die in a war, alongside the fighting, the blockades, the breakdown of normal life, and much else. The researchers do not claim the anomaly was the only reason deaths rose, or even the main one. What they show is that the climate signal and the mortality signal move together 3 times over in a way that is hard to dismiss as chance. The weather earned a place on the list of things killing people. It did not push everything else off the list. There is a quiet lesson in this part of the story about how disasters stack. We tend to file events under single causes. This was a war, that was a pandemic, the other was a famine. The Ice Core argues for a messier and more truthful picture, in which a stuck weather pattern, a long war, food shortages, and a coming virus all pressed on the same people at the same time, each one making the others worse. The death peaks were not the work of any single hand. They were what happened when several hands pushed together. So by the late stages of the war, the stage was fully set. A weakened, crowded, hungry, chilled population stretched across a continent, its defences worn thin by years of relentless weather, with the dying already running above normal. Into that exact situation came a new strain of influenza, the H1N1 virus that the world would remember as the Spanish flu. Where it came from, and why its first appearance was so much milder than what followed, is the next part of the story. The influenza that would eventually kill at least 50 million people did not announce itself. When the virus, a strain of H1N1, first moved through populations in the spring of 1918, it behaved much like ordinary flu. People got sick, most recovered, and life went on under the larger shadow of the war. This first wave was real and widespread, but it was not the monster the world would meet later that year. At the time, there was little reason to think this particular flu would become the deadliest single outbreak ever recorded. Where it began is a question with several proposed answers, and honesty requires holding them loosely. The study leans on earlier research suggesting the first European wave most likely arrived with Allied troops coming into France from Asia during the fall and winter of 1917. That is one credible account of how the virus reached the Western Front and spread from there. Other researchers have pointed to other possible starting points elsewhere in the world. The exact birthplace of the pandemic remains genuinely uncertain, and the careful thing to say is that it is not settled. What is clear is that by the spring of 1918, The virus was loose among the armies and the civilians of a continent already under strain. The name the world hung on it, Spanish flu, is a misnomer worth correcting briefly, because it shows how confused the picture was at the time. The disease was not Spanish in origin. Spain was neutral in the war, and its newspapers reported freely on the spreading illness, while the warring countries censored their own press to keep up morale. Because the news came out of Spain, the flu got Spain's name, unfairly. The label stuck for a century, attached to a virus that almost certainly started somewhere else entirely. The first wave's mildness is part of what makes the later horror so striking, and it connects back to the weather in a specific way. A virus moving through a population in spring, as conditions are warming and people are spending more time outdoors and apart, faces a harder road than the same virus in cold, crowded indoor conditions. The spring wave spread, but it did not yet have the full set of advantages that would later make it so lethal. It was a warning that went largely unheard, partly because the war drowned out almost everything else, and partly because the disease at that point looked survivable. What the spring wave did do was seed the virus widely, putting it into armies and cities and supply lines all across Europe and beyond. Soldiers carried it as they moved. Crowded camps and trains and hospitals passed it along. By the time the wave faded with the warmer months, the virus was no longer a local problem. It was everywhere people were waiting, and the conditions that would let it explode were already gathering for the autumn. It is worth pausing on how ordinary the beginning was, because it carries a lesson that has not aged. The deadliest pandemic in recorded history opened quietly, with a wave of illness mild enough that most people, distracted by a world war, did not grasp what they were looking at. The danger was not obvious at the start. It built. The gap between the unremarkable spring and the catastrophic autumn is one of the hardest things to absorb about 1918, and it is a reason later generations have learned to watch new flu strains carefully even when they seem mild at first. The turn from mild to monstrous happened in the second half of the year, and this is where the climate story and the disease story finally meet head-on. The deadliest wave of the pandemic in Europe began in the autumn of 1918, and it followed close behind a renewed stretch of cold temperatures and heavy rain, one of those surges the Ice Core had recorded. The weather and the virus, which had been running on separate tracks, arrived at the same place at the same time. What happened when they met is the centre of the whole story, and it is where we turn next. The autumn of 1918 is when the pandemic became the catastrophe history remembers. The second wave of the H1N1 virus was far deadlier than the first, striking with a ferocity that shocked doctors who thought they knew what influenza could do. It killed not only the old and the frail, as flu usually does, but also young, healthy adults in the prime of life, sometimes within days of the first symptoms. This was the wave that drove the toll toward at least 50 million people worldwide, the highest known death count for any single pandemic. The detail that ties it to the climate story is the timing. The study found that this deadliest wave in Europe began closely following a period of heavy precipitation and cold temperatures, another surge of the same stuck pattern the Ice Core had been recording for years. The weather turned cold and wet, and right behind it the virus turned lethal on a massive scale. After 3 earlier death peaks that had tracked the cold, wet surges, here was a fourth and far worse convergence, the virus and the weather peaking together in the same months. The autumn of that year shows a double peak in both deaths and rainfall, rising together, easing together, rising again. Why would cold and rain push a flu wave from bad to catastrophic? The mechanisms are ordinary and they stack. Cold, wet weather drives people indoors and packs them together, which is exactly the close shared air a respiratory virus needs to spread fast. The same conditions strain the body, making it easier for the virus to take hold and harder to fight off. A population already worn thin by years of the anomaly, by war, by hunger, and by the earlier waves of dying, had little reserve left to resist. The virus arrived at the worst possible moment, into the worst possible conditions, in people with the least possible strength to endure it. It is important to be precise about what the study claims here, because it is easy to overshoot. The researchers are not saying the weather created the virus, or made it more dangerous at the level of its biology. They are saying the cold, wet conditions helped the virus spread and helped it kill, by crowding people, by weakening them, and by stripping away whatever defences they had left. The virus brought its own lethality. The weather handed it a population perfectly primed to be devastated. Both were needed for the scale of what happened. The convergence is the reason this story is worth telling as one story rather than two. For years, a war and a weather anomaly had been grinding down a continent. Then a new virus, already seeded by the mild spring wave, met a fresh surge of cold and rain in the autumn, falling on people who had nothing left to give. War, weather and disease did not take turns. At the climax, they landed together, and the combined blow was far heavier than any one of them would have been alone. The 50 million is the measure of what that combination could do. There is a sober point to draw, and it should be drawn calmly. The same virus, arriving in a rested, well-fed, peaceful population in mild conditions, might still have caused a serious pandemic, but the evidence suggests the death toll was magnified by the circumstances it found. Biology set the floor of the danger. Weather and war raised the ceiling. That is a more careful and more useful way to understand 1918 than treating the virus as an unstoppable force that would have killed 50 million no matter what. The conditions mattered, and the ice core lets us measure that they did. The number itself, that figure of at least 50 million dead, deserves a closer and more honest look than it usually gets. It is one of the largest death tolls ever attached to a single event, and yet it is also an estimate with real uncertainty around it, and a story behind how it was reached. Understanding where the number comes from, and why it is both trustworthy and rough, is the next piece of the picture, and it keeps us honest about everything that came before. The figure that gives this story its weight is the toll of the pandemic. At least 50 million people dead, with some estimates reaching higher still. It is worth saying clearly that this is an estimate, not a head count. No one stood at the end of 1919 with a complete and accurate ledger of every death from the flu across the entire world. The number was assembled afterward, painstakingly, from incomplete records, and it carries real uncertainty. That does not make it untrustworthy. It makes it honest to treat with care. Several things make counting hard. The pandemic struck during and just after a world war, when normal record-keeping had broken down across much of the globe. Many of the hardest hit places had little in the way of death registration to begin with. The flu often killed indirectly, through pneumonia and other complications, so deaths could be recorded under other causes. And in the chaos of 1918, with hospitals overwhelmed and officials distracted, a great many deaths were simply never properly logged at all. Every one of these gaps pushes the true number into a range rather than a single certain figure. The way historians and epidemiologists handle this is to work from the records that do exist, and to estimate carefully for the places where records are thin. Early counts after the pandemic landed around 20 million dead. As researchers went back over the decades, with better methods and access to more records, the estimates climbed. The figure of 50 million became the widely accepted lower bound, and some careful studies have argued the real total could be higher, perhaps far higher in parts of the world that were barely counted at the time. The number grew not because the pandemic got worse, but because our accounting of it got better. To feel the scale, set the toll against the war that framed it. The First World War, one of the deadliest conflicts in human history up to that point, killed roughly 20 million people across more than 4 years of industrial slaughter. The influenza killed at least 2.5 times that many in a fraction of the time, much of it concentrated into a few terrible months in late 1918. A disease most people thought of as a seasonal nuisance outpaced the largest war the world had ever fought, and it did so largely out of the headlines, overshadowed by that very war. The pandemic also infected far more people than it killed, which is its own staggering figure. Estimates suggest something like 500 million people were infected, at a time when the entire human population was well under 2 billion. That means a large share of everyone alive caught this virus within about 2 years. The death toll, as enormous as it is, sat on top of a wave of illness that touched a substantial fraction of humanity. The scale is hard to hold in the mind, which is part of why the event faded from common memory for so long. Holding the uncertainty and the scale together is the honest position, and it is the one the careful sources take. We can say with confidence that the toll was catastrophic, almost certainly at least 50 million, very possibly more, and that it ranks as the deadliest single pandemic in recorded history. We cannot give a precise figure to the last million, and anyone who offers one with false confidence has stopped describing the past and started decorating it. The 50 million is a floor we trust, not a ceiling we have measured. This care about the number matters for the larger argument, because the whole point of the ice core study is to be precise about cause and effect. If we're going to say a weather anomaly helped magnify a death toll, we have to be honest about how well we know that toll in the first place. The answer is that we know it well enough to be sure it was immense, and roughly enough that we should speak of ranges and estimates rather than exact counts. That same honesty applies to one of the easiest mistakes a story like this can invite: the mistake of thinking the weather somehow carried the disease. Clearing up exactly what the air did and did not do is the last piece of the first half. There is a tempting and wrong way to hear this whole story, and it is worth taking apart plainly, because the rest of the report depends on getting it right. The tempting version goes like this. The air over Europe behaved strangely for 6 years, and during those same years 50 million people died of the flu. So the strange air must have brought the disease. That is the wrong reading. The weather did not carry the virus. The marine air streaming over the continent was not laced with influenza. The salt in the ice is a record of wind and ocean, not of contagion. What the weather actually did was act on 2 fronts at once, and neither of them involved transporting the virus. On the first front, it pressed on people directly, through cold, rain, hunger, and exposure, killing some outright and weakening many more, as we have already seen. On the second front, it shaped the conditions in which the virus, once it arrived on its own, could spread and kill. Cold, wet weather pushed people indoors and crowded them together, gave a respiratory disease the close shared air it thrives in, and lowered the defences of bodies already worn thin. The air was not a courier. It was an accomplice. Holding that distinction clearly is what separates a real scientific claim from a superstition. Plenty of old beliefs blamed bad air itself for disease, imagining that sickness rode in on foul winds. The ice core study is making a more careful and more modern argument. It says that a measurable climate anomaly created physical and social conditions, the crowding, the chill, the hunger, the weakened immunity, that allowed a virus spreading by its own means to do far more damage than it otherwise could. The weather set the table, the virus ate. The same logic explains the deaths that came before the flu without any virus at all. Recall that mortality in Europe rose and fell with the cold, wet surges 3 times before the pandemic peaked. Those earlier deaths were not influenza. They were pneumonia, exposure, infection, and the slow toll of hunger and hardship, driven by the weather acting directly on vulnerable people. The anomaly was already a killer on its own terms, through ordinary mechanisms, well before the H1N1 virus turned lethal. That is a clean demonstration that the weather did real harm by itself, not by carrying any disease. There is a piece of this study, though, that does involve the weather influencing the virus more directly, and it is the most speculative part of the whole picture. It concerns not the spread among people, but the behaviour of the animals that carry influenza in the wild. Flu viruses like H1N1 live naturally in waterfowl, in ducks and similar birds, and those birds normally migrate with the seasons. The researchers raised the possibility that the climate anomaly disrupted that migration, keeping the birds near people instead of moving them along, and that this could have affected how the virus passed between the animal world and the human one. That idea is genuinely interesting, and it is also clearly marked, in the study and here, as a hypothesis rather than a proven fact. It is a thread worth following carefully, with all its uncertainty kept in view, because it is the one place where the weather might have touched the virus itself rather than just the people it infected. We will take it up properly in the second half, along with the harder questions of how solid the whole ice core reading really is, how it holds up against the rest of the evidence, and what, if anything, it means for the sky above us today. For now, the first half leaves us with a clear and careful picture. A stuck Atlantic weather pattern, recorded in Alpine ice, flooded Europe with cold ocean air for 6 years. That air killed directly through cold, rain, and hunger, and it primed a continent to be devastated when a new flu virus arrived and met a fresh, cold, wet surge in the autumn of its worst year. The weather did not bring the disease. It built the conditions that let the disease become a catastrophe. The second half is where we test that picture, push on its weak points, and ask what it tells us now. To make sense of why a stuck weather pattern could turn a flu into a catastrophe, It helps to slow down and look at how a respiratory virus actually moves between people. Influenza spreads through the air we share. When a sick person breathes, coughs, or speaks, they release tiny droplets carrying the virus, and anyone close enough to breathe that same air can take it in. The closer people are, the longer they share a space, and the less fresh air moves through it, the easier the virus finds its next host. Everything about how a flu spreads comes back to shared, close, stale air. Now lay the anomaly over that simple fact. Cold, wet weather does one thing above all to human behaviour. It drives people inside and packs them together. When it is freezing and pouring for weeks on end, people crowd into whatever warm, dry shelter they can find, and they shut the doors and windows against the cold. That is the exact opposite of what slows a respiratory virus. The weather was herding people into the close, shared, poorly aired spaces where influenza spreads best, and it was doing it across a whole continent at once. The crowding was worse in 1918 than almost any other time because of the war. Soldiers lived jammed together in barracks, trenches, trains, and field hospitals. Cities were swollen with workers and refugees. Supply lines moved not just food and weapons, but people, constantly, from one crowded place to another. A virus could hardly have asked for a better network to travel through, and the cold, wet weather only tightened the crush by keeping everyone indoors and close. Cold does a second thing, quieter, but real. It wears down the body's defences. A person who is chronically cold, damp, and underfed is a person whose immune system is already working at a disadvantage. The lining of the nose and airways, the body's first barrier against an inhaled virus, works less well when a person is chilled. Add years of poor nutrition from ruined harvests, and the exhaustion of war, and you have bodies that catch the virus more easily and fight it less successfully once they have it. The same conditions that spread the virus also softened the people it reached. There is a third effect worth naming, and it is about the strain on care. When a population is already sick and dying from cold, exposure and pneumonia, the people and places meant to help the ill are overwhelmed before the pandemic even crests. Doctors, nurses, hospital beds, and medicines were all in short supply and stretched thin by the war and the weather long before the deadly autumn wave hit. A virus that lands on a healthcare system already at its limit kills more people than the same virus landing on one with room to respond. Put these together, and the mechanism is complete, without any need for the weather to carry the disease. Cold and rain crowded people indoors, weakened their bodies, strained their food and care, and did all of this for years, so that when the virus surged in the autumn of its worst year, it met the most favourable possible conditions. More hosts, packed closer, breathing shared air, with lower defences and less help available. Each of those is an ordinary, well-understood factor in how flu spreads. The anomaly simply turned all of them up at once and held them there. This is why the study can connect a climate signal to a death toll without claiming anything mystical. The links are mundane, which is exactly what makes them believable. We do not need the air to be poisoned or the virus to ride the wind. We only need cold, wet weather to do what cold, wet weather always does to crowded, hungry, exhausted people, which is to make a contagious respiratory disease spread further and kill more. The 50 million is what that ordinary machinery produced when it ran at full strength across a continent for years. There is, though, one way the weather may have reached past the people and touched the virus closer to its source, in the wild animals that carry influenza when it is not in us. This is the most speculative thread in the study, and also one of the most intriguing, because it asks whether the anomaly changed where the virus lived before it ever reached a human lung. It centres on a familiar bird, the duck, and on the long journeys ducks make each year. That thread is worth following next, carefully, with its uncertainty held in plain view. Influenza is not, at its root, a human disease. The natural home of flu viruses, including the H1N1 family behind the 1918 pandemic, is in wild birds, especially waterfowl like ducks. These birds carry many flu strains in their guts, usually without much harm to themselves, and they shed the virus into the water where they gather. From that wild reservoir, flu can occasionally jump into other animals and into people, sometimes after mixing and changing along the way. The ducks are the deep well the virus keeps returning to. Waterfowl are also great travellers. Many species migrate long distances with the seasons, flying between breeding grounds and wintering grounds along well-worn routes. As they move, they carry their viruses with them, spreading flu strains across continents and bringing different strains into contact. Where the birds are and whether they are moving or staying put helps determine where the virus is and what it might do. The annual migration is part of how influenza is distributed across the world. Here is where the climate anomaly enters as a hypothesis. The researchers noted that mallards, one of the common ducks that carry influenza, are known to be sensitive to climate anomalies in their migration. Bad enough weather can disrupt the timing and the routes of migration, and one of the team members suggested that during the 6-year anomaly, the birds likely stayed put for much of that period, rather than moving on as they normally would. If the ducks stopped migrating away, and instead lingered near where people were, that could have kept the wild reservoir of the virus close to human populations for longer than usual. The possible consequence is the interesting part. If infected waterfowl stayed near people, near the armies and the towns and the farms, rather than flying off along their usual routes, then the chances for the virus to pass from birds into people, or into the pigs that can act as a mixing vessel, may have been raised. In this picture, the anomaly did not just shape how the virus spread among humans, it may have helped keep the virus's animal source parked in the wrong place at the wrong time, near a vulnerable population, during the exact years the pandemic took hold. It is essential to be honest about how speculative this is, and the study itself treats it as a suggestion rather than a finding. We have strong evidence that the climate was anomalous, that the weather killed directly, and that the deadly flu wave followed a cold, wet surge. We do not have direct evidence tracking individual duck migrations in 1918, or measuring exactly how the birds' movements changed, or proving that altered migration fed the pandemic. The duck hypothesis is a plausible mechanism built on what we know about how mallards respond to weather, not a documented chain of events. It belongs in the story marked clearly as a maybe. What makes it worth including, despite the uncertainty, is that it points at something real about how climate and disease connect. Diseases that live in animals are shaped by where those animals go, and where animals go is shaped by weather and climate. This is not a quirk of 1918. It is a general principle that matters more and more as the climate shifts. If changing conditions move animals, or change which animals are where, they can change the map of where diseases sit and how they reach people. The duck idea is a single old instance of a pattern scientists now watch broadly. So the thread leaves us with two things held together. There is a clean, well-supported core, the anomaly, the direct deaths, the cold, wet surge before the deadly wave, and the crowding and weakening that spread and worsened the flu among people. And there is a more speculative edge, the possibility that the same weather held the virus's animal reservoir close to humans by stalling bird migration. The first we can lean on. The second we note with care, neither dismissing it nor leaning our weight on it. That careful weighing of what is solid and what is suggested is exactly the right frame for the next question, which is the most basic one of all. How much should we trust a story built so heavily on a single column of ice from one mountain? An entire argument rests on reading those frozen layers correctly, so it is fair and important to ask how the team read them, how sure they could be, and what the limits of that reading really are. Everything in this story leans on one physical object, a core of ice drilled from one glacier, and it is fair to ask how much weight a single core can bear. The honest answer is that the team had to be careful about exactly that, and the care they took is part of why the result holds. An ice core is not a simple ruler. Reading it well means understanding how the ice forms, how it gets distorted, and where the reading is firm and where it goes soft. Start with how the layers form. Each year, snow falls on the glacier and is later buried by the next year's snow. In principle, that gives a yearly layering, like rings in a tree, that a scientist can count down through time. At the top of the glacier, where the layers are young and have not been squeezed much, this works cleanly. The annual bands are thick and easy to tell apart, and dating them is straightforward. The trouble grows with depth. As you go deeper, the weight of all the ice above presses the older layers thinner and thinner. Years that were once a comfortable thickness get squeezed down until they are hard to separate. At the depths holding the 1914 to 1919 window, the team worked with a stated possible error of about 1 year in either direction. That means a feature they place in, say, 1916 might truly belong a year earlier or later. They did not hide this. They stated it, which is what careful science looks like. A margin of about a year sounds like it could wreck a story that turns on specific years. It does not, and the reason is the length of the signal. The anomaly was not a single sharp spike that a one-year error could smear into meaninglessness. It was a sustained 6-year stretch of high salt, cold, and rain. A signal that broad does not vanish or move wildly inside a one-year wobble. You might argue about whether a particular peak fell in one year or the next, but you cannot argue away a 6-year pattern that sits clearly above everything around it. The error matters for fine detail, not for the big shape. There is a deeper worry about any single core, which is whether one spot on one mountain really speaks for a whole continent. A glacier in the Alps catches the air that reaches it, which is mostly air arriving from the west and north over Europe. That happens to make it a reasonable listening post for exactly the kind of marine air influx the study is about. Still, one site is one site. If the entire argument rested on the salt in this core alone, a skeptic would be right to hold back. A clever reading of one record is a hypothesis, not a conclusion. This is precisely why the team did not stop at the ice, and why the study is more robust than a single core would allow. They treated the core as one witness among several, to be cross-examined against others. The ice proposed a story that the air was abnormally cold, wet, and marine for 6 years. The next step was to ask whether completely independent records, gathered by other people for other reasons, told the same story. If they did, the core's reading would stand on far more than its own layers. If they did not, the whole idea would deserve doubt. The honest framing, then, is that the ice core is the spark but not the entire fire. It is a high-quality, well-dated record with a clearly stated margin of error, strongest for the broad shape of a multi-year event and humble about fine yearly detail. It pointed the researchers toward a specific, testable claim about Europe's climate in those years. The value of that claim depends on whether it survives contact with the rest of the evidence. So the right question is not whether to trust one core, but whether the world's other records agree with it. They do, and that agreement is what turns an interesting reading into a credible argument. The independent measurements of temperature, the rainfall records, and the careful counts of the dead, all kept separately from the glacier, line up with what the ice says. Walking through how well those records match, and why their agreement matters so much, is the next step in testing whether this whole picture deserves the confidence the study places in it. A single record can fool you. Agreement among independent records is much harder to dismiss, and it is the backbone of the case the study makes. The ice core proposed that Europe was abnormally cold, wet, and washed in marine air from 1914 to 1919. To test that, the team set the core's story beside 3 other kinds of evidence, each gathered separately by different people, for reasons that had nothing to do with glaciers. The question was simple: do the others agree? The first independent check was temperature. Across Europe, people had been measuring and recording temperatures with instruments well before 1914, in many countries and many cities. Those measurements were not made to study ice cores or pandemics. They were just the ordinary weather records of the time. When the team looked at them across the war years, they found the cold the ice had implied. The thermometers confirmed that those years ran unusually cold over the continent, matching the marine air influx the salt had recorded. 2 unrelated systems, one chemical in a glacier and one mechanical in weather stations, told the same story about the temperature of the air. The second check was precipitation. Rainfall was likewise measured and logged at the time by weather observers across Europe, again for everyday reasons. The ice core's account demanded that those years be wet, because marine air pouring over the continent brings rain. The rainfall records bore that out. The wet years in the gauges lined up with the salty years in the ice, and crucially, the timing within the years matched too. In the autumn and winter of 1918, precipitation peaked in a way that fit the deadly turn of the pandemic, with a notable peak in October, a slight easing in November, and another peak in December. The third check, and the most important for the human story, was mortality. The team gathered records of deaths across 13 European countries, official tallies kept by governments for administrative reasons, entirely separate from any climate record. When they laid those death counts against the climate signal, the two moved together. mortality rose during and just after the cold, wet surges, 3 times across the war, and then again in the deadly autumn of 1918. The deaths even showed the same double peak in that autumn that the rainfall did, the two rising and falling almost in step. Step back and consider what this convergence means. 4 different windows onto the same years, the salt in the ice, the temperature readings, the rainfall logs, and the death registers all point the same way. They were not built from one another. The glacier did not know what the thermometers said. The death clerks were not consulting rain gauges. Each record was made on its own, and yet they agree on the shape of those years: cold, wet, and deadly, with the worst convergence in the autumn of 1918. That kind of independent agreement is the strongest argument a study like this can offer. It is the difference between one person's account and 4 witnesses who never spoke to each other telling the same story. If a single witness describes an event, you weigh their reliability and reserve some doubt. If 4 witnesses, with no chance to coordinate, all describe the same event the same way, the account becomes very hard to wave off. The study's strength is not that the ice core is perfect. It is that the ice core's story survives comparison with 3 other completely separate records, and they all reinforce it. This is also what protects the argument from the natural suspicion that the researchers simply found a pattern they were hoping to find. The death records and weather logs existed long before anyone drilled this core. They could just as easily have contradicted the ice, in which case the study would have had to admit the core was misleading. Instead, they matched. The pattern was not imposed on the data. It was found sitting in several independent datasets at once, which is exactly what a real signal does, and a wished-for one rarely does. With the case now resting on agreement rather than on a single clever reading, a new and broader question opens up. If a stuck Atlantic pattern like this could settle over Europe for 6 years in the early 20th century, was that a freak event that happened once, or is it something the climate does from time to time? The same ice core offers a first answer because it reaches back far past 1914 and forward past 1919. What it shows about other years is the next thing to examine. One of the quietly important findings in this study is easy to miss, because it sits in the background of the dramatic war years. The same ice core that recorded the 1914 to 1919 anomaly also recorded the decades before and after it, and in that longer record this kind of climate event shows up more than once. The stuck, cold marine pattern was not a single freak that happened exactly once and never again. The ice indicates that similar events have occurred several times, both before the war and since. That changes how we should think about the anomaly. If it were a true one-of-a-kind event, we might file it as a historical curiosity, a strange alignment that produced a catastrophe and then never recurred. But the core says otherwise. This is a recurring mode of the climate, something the North Atlantic system falls into now and then. The pattern has a shape the atmosphere knows how to make, and it makes it periodically when conditions line up the right way. What set the war years apart, then, was not that the pattern existed, but how strong and how long it was. Across the full century the core covers, the 1914 to 1918 episode was the strongest of its kind. Other episodes happened, but this one reached further and held longer, the most extreme version in 100 years. So the right way to understand it is not as a unique freak, but as the worst instance of a recurring event, an unusually severe flare of something the climate does on a smaller scale fairly often. This distinction matters for everything that follows, so it is worth fixing firmly. A unique event teaches us little about the future, because by definition it does not repeat. A recurring event, even one that rarely reaches an extreme, is something we can study, expect, and watch for. The ice core moves the 1918 anomaly out of the first category and into the second. It tells us this is a normal, if occasional, behaviour of the Atlantic atmosphere, which means it is the kind of thing that can and will happen again, though almost always in milder form. There is independent support for the idea that the North Atlantic falls into stuck, cold patterns from time to time. Climate scientists have documented other multi-year stretches when blocking patterns, and a wandering Iceland low-pushed unusual conditions onto the surrounding regions. One well-studied example is a period in the early 1960s, when several years of enhanced blocking over Greenland reshaped conditions across the North Atlantic, with effects that rippled into the ocean for years afterward. These episodes are part of the normal, if irregular, repertoire of the system. The atmosphere has these moods, and it returns to them. None of this should be heard as alarming, and it is important to keep the tone level here. The fact that the pattern recurs does not mean a repeat of 1918 is coming. The vast majority of these episodes are far milder than the war years, and even the war years became a catastrophe only because of everything else happening at the same time: the World War, the hunger, the new virus, and the absence of modern medicine. The recurrence of the weather pattern is a fact about the atmosphere. It is not, by itself, a forecast of disaster. What the recurrence does give us is something more useful than fear, which is the ability to recognise the pattern when it appears. Because it has happened before and since, scientists know its fingerprints: the wandering Iceland low, the weakened westerlies, the surges of cold marine air. They can spot a version of it forming in the modern record, measure it, and understand it as a known mode rather than a mystery. That recognition is the first step toward not being caught off guard the way the world was a century ago. In fact, a clear modern example sits within living memory, recent enough that many people remember living through it. Not long ago, a single hard winter showed exactly the kind of Iceland low displacement that drove the war years, in a milder and shorter form. Looking at that recent winter closely is the best way to see that this pattern is not ancient history at all, but a live feature of the climate we live in now. That winter is where we turn next. You do not have to reach back a century to see the Iceland low sitting in the wrong place. It happened within the memory of most adults alive today, in the winter that bridged the years 2010 and 2011, when parts of northern and western Europe were gripped by exceptional cold. For anyone who lived through it, the images are familiar: snowbound airports, frozen roads, towns dug out from under far more snow than they were used to. The cause, in the language of this story, was the same kind of displacement that the ice core recorded for the war years. In a normal winter, the Iceland low sits west of Iceland, and the westerly winds carry mild Atlantic air over Europe. During that winter, the low shifted, appearing regularly to the east of Iceland instead. At the same time, a strong area of high pressure built over Greenland. That combination reversed the usual flow. Instead of mild ocean air sweeping in from the west, the door opened to the north, and exceptionally cold Arctic air poured down into Western Europe. The guard had stepped away from the door exactly as it had a century before, only this time for a season rather than for years. This is the same machinery described earlier, caught in the act in the modern record. The pattern was what scientists call a negative phase of the North Atlantic Oscillation, the mode where the pressure difference that drives the westerlies collapses, the steady west to east flow weakens, and cold northern air finds its way south. It came alongside a blocking high over Greenland, a stubborn region of high pressure that sat in place and forced the weather systems to detour around it, which is part of how these patterns lock in and persist. The textbook setup for a cold European winter was on full display. The winter of 2010 and 11 also came during a La Niña, a periodic cooling of the tropical Pacific Ocean far away across the world. La Niña events are often associated with a negative North Atlantic Oscillation, the very phase that brings cold, wet conditions to parts of Europe. This is a useful reminder that the Atlantic engine does not run in isolation. It is nudged by conditions in distant oceans, by the state of the tropics, and by other large patterns, all of which can tip it toward one mode or another. The cold European winter had roots reaching all the way to the Pacific. The point of bringing in this recent winter is not to equate it with the war years, because the two are not equal. The 2010 and 11 cold was a single hard season, severe and disruptive, but brief, falling on a modern Europe with central heating, stocked shops, antibiotics, and functioning healthcare. It caused travel chaos and hardship and some deaths among the vulnerable, as hard winters do, but nothing remotely like the sustained 6-year grinding of a century earlier. The comparison is about mechanism, not about scale. The same kind of pattern, in a vastly different world, produces vastly different consequences. That contrast is actually reassuring, and it is worth letting it land calmly. The 1918 catastrophe required the weather pattern, yes, but it also required everything else: a continent at war, food running short, no modern medicine, and a brand new virus arriving at the worst moment. Strip away those other factors, as the modern world has largely done in wealthy regions, and the same atmospheric pattern produces a difficult winter rather than a demographic disaster. The weather can still misbehave the old way. The world it lands on has changed. What the recent winter proves is simply that the pattern is alive and current. The displaced Iceland low, the Greenland block, the negative oscillation, the cold pouring south, all of it is part of the climate we live in now, not a relic of the past. Scientists can watch it form in real time with modern instruments, far more detailed than a single ice core, and understand it as it happens. That ongoing reality raises a natural curiosity about whether anything unusual is happening in the North Atlantic today, and there is in fact a strange, persistent feature in that ocean right now that has drawn a great deal of attention. It is called the cold blob, and it is worth a careful look. While most of the planet has been warming, there is one stubborn patch of ocean that has been doing the opposite. In the North Atlantic, south of Greenland, sits a region of sea surface that has been cooling, or at least failing to warm, even as the waters around it and the world as a whole grow hotter. Scientists have nicknamed it the cold blob. It stands out clearly on maps of ocean temperature change, a cool spot in a warming sea, and it has become one of the more closely studied features of the modern North Atlantic. The reason it draws attention is that the North Atlantic is a key part of the planet's ocean circulation, the great system of currents that moves heat around the globe. One major piece of that system carries warm water northward near the surface and returns cold water southward in the deep, helping to keep Europe milder than its latitude would otherwise allow. A persistent cold patch in just the place where that circulation does important work naturally raises questions about whether the circulation is changing and what that might mean for the weather downstream. The cold blob has often been linked to changes in ocean circulation, the idea being that a slowing of the northward heat transport would leave that region cooler than expected. That remains one leading explanation. But research has added an important wrinkle, and it ties directly back to this whole story. A study found that changes in large-scale atmospheric patterns may play an equally important role in creating and maintaining the cold blob, alongside the ocean changes. The same kind of atmospheric behaviour that runs through this entire report, the shifting pressure systems and wind patterns over the North Atlantic, appears to be part of what shapes that cool patch of sea. This is the deep connection worth drawing out, calmly and without overstating it. The atmosphere and the ocean over the North Atlantic are not two separate machines. They are one coupled system, each pushing on the other. The winds set by the Iceland low and the Azores high stir the ocean surface, move heat and shape currents. The ocean's temperature in turn feeds back on the air above it, nudging the pressure patterns and the winds. The cold blob sits right at the heart of that conversation, a place where ocean and atmosphere are clearly talking, and where untangling which is leading and which is following is genuinely hard. It is important to be measured about what the cold blob does and does not tell us, because it is a topic where speculation runs ahead of evidence. The honest state of the science is that the cold blob is real and well observed, that it likely reflects some combination of ocean circulation changes and atmospheric pattern changes, and that researchers are still working out the balance between those causes and the long-term implications. It is an active question, not a settled one. Anyone claiming certainty about exactly what it means for the future has moved past what the evidence currently supports. The cold blob matters to this story for a specific and limited reason. It is concrete, present-day evidence that the North Atlantic system, the same system that jammed for 6 years a century ago, is dynamic and capable of surprising behaviour right now. The ocean and air over that part of the world are doing something unusual that scientists are watching carefully. That is not a cause for alarm, but it is a reason for attention. The machinery behind the 1918 anomaly is not a fossil. It is operating today, with its own modern quirks. All of this points toward a question that has been waiting in the background of the whole report. What actually makes the Atlantic engine shift between its moods, and what could push it into a stuck pattern like the one that marked the war years? The answer involves several forces, some close to home, and some reaching from the far side of the planet and even from the sun. Laying out those drivers honestly, including how much we do and do not understand them, is the next step. A fair question runs underneath this entire story. If a stuck cold pattern over the North Atlantic can do so much harm, what makes the system shift in the first place, and what could lock it into one mood for years? The honest answer is that several forces nudge this engine, that they interact in complicated ways, and that scientists understand some of them well and others only partly. Laying them out plainly, without pretending to more certainty than exists, is the careful thing to do. One important driver comes from high above, in a part of the atmosphere called the stratosphere. Far over the poles in winter, a circle of strong winds called the polar vortex normally pens cold air near the top of the world. Sometimes that vortex is suddenly disrupted, in an event scientists call a sudden stratospheric warming, when the high-altitude air over the pole warms sharply and the vortex weakens or breaks apart. In the weeks that follow, the effects can press downward into the lower atmosphere where our weather lives, often tipping the North Atlantic Oscillation toward its negative phase. That negative phase, as we have seen, is the one that weakens the westerlies and opens the door to cold air over Europe. A second driver sits closer to our level, in the form of blocking highs. A blocking high is a large, stubborn region of high pressure that parks itself and refuses to move, forcing the normal flow of weather systems to detour around it. When a block sets up in the right place, often over Greenland or nearby, it can hold a cold pattern in place over Europe for days or weeks, and repeated or persistent blocking is part of how a short cold spell becomes a long one. Blocking is, in a real sense, the atmosphere getting stuck, and it is central to how a passing pattern turns into the kind of persistent one this story is about. A third driver reaches from the far side of the planet, in the tropical Pacific. The periodic cooling there known as La Niña, and its warm counterpart El Niño, send ripples through the global atmosphere that reach all the way to the North Atlantic. La Niña in particular is often associated with the negative phase of the North Atlantic Oscillation, tilting the odds toward cold, wet European conditions. This is why the distant Pacific keeps appearing in a story about European weather. The atmosphere is global, and a change in one ocean can lean on the pressure patterns over another. There is even a possible role for the sun, and it is worth mentioning precisely because it must be handled with care. Some research has explored links between long-term changes in solar activity and the behaviour of the North Atlantic Oscillation. This is a real area of study, but it is also one where claims have often outrun evidence, and where the connections, if real, are subtle and debated. The responsible way to include the sun is to note that it has been investigated as one possible background influence, while being clear that it is far from a settled or dominant cause. It is a maybe at the edge of the picture, not a lever someone is pulling. The crucial honest point is that no single one of these forces fully explains the 6-year anomaly of the war years. We can name the kinds of drivers that shift the Atlantic engine, the stratosphere, the blocking highs, the tropical oceans, and possibly the sun. We can say that some combination of them must have conspired to hold the pattern stuck for so long. What we cannot do, with the evidence in hand, is reconstruct the exact recipe that produced that specific event, or predict confidently when such an extreme might recur. The persistence of the war years remains, in its deepest cause, partly an open question. That admission is not a weakness in the story. It is the difference between science and superstition. We understand the machinery and its main influences well enough to recognize the pattern and to know it can return. We do not understand it well enough to forecast its worst extremes far in advance. Holding both of those truths at once is exactly right, and it leads directly to the question that hangs over the whole subject in an era of climate change, which is whether a warming world makes patterns like this more or less likely. That is the next thread, and it too calls for care. The obvious modern question is whether climate change makes a stuck pattern like the one behind 1918 more likely, and it deserves a careful and honest answer rather than an easy one. The truthful response is that scientists are actively studying how a warming world affects North Atlantic patterns, that there are real reasons to expect changes, and that the details remain genuinely uncertain. This is a frontier of research, not a closed case, and the honest stance is to say what is known while clearly marking what is not. What is well established is that the climate is warming, and that warming reshapes the conditions in which all these patterns operate. The Arctic in particular is heating faster than the rest of the planet, which shrinks the temperature difference between the pole and the mid-latitudes. That difference is part of what drives the strength and steadiness of the westerly winds and the jet stream. Reduce it, and there is reason to think the flow could become more prone to waviness and to getting stuck, which is exactly the kind of behaviour behind blocking and persistent patterns. This is a plausible mechanism, and it is taken seriously, but plausible is not proven, and here the honesty has to be firm. Whether a warming Arctic actually makes blocking and stuck patterns more frequent over the North Atlantic is a question scientists are still debating, with evidence pointing in different directions and models not fully agreed. The North Atlantic oscillation itself has been hard to predict and hard to pin down, with its behaviour shifting in ways that are not yet fully explained, including changes in where the Iceland low likes to sit. Anyone who tells you confidently that climate change will definitely make European cold snaps more or less common is going beyond what the science currently supports. There is a further complication that cuts against simple fear, and it deserves equal weight. Even if a stuck cold pattern did set up over a warming Europe, it would be setting up over a warmer baseline. A cold anomaly added to a warmer world is not the same as a cold anomaly added to the cooler world of a century ago. The same atmospheric pattern could produce milder absolute cold than it once did, even as it brings unusual conditions relative to what people now expect. Warming changes not just the odds of patterns, but the temperatures they deliver, and that interaction is part of what makes confident predictions so hard. The most important point, though, has nothing to do with the weather pattern itself and everything to do with the world it would land on. The catastrophe of 1918 was never the work of weather alone. It took a stuck pattern and a world war and widespread hunger and the absence of modern medicine and a dangerous new virus all at once. The weather was one ingredient among several, and arguably not the decisive one. A similar pattern landing on today's world, with its medicine, its food systems, its forecasting, and its public health, would meet a vastly more resilient target. The same sky does not produce the same death toll when the ground beneath it has changed so much. This is why the right reaction to all of this is attention rather than alarm, and the distinction is not a matter of mood but of accuracy. The science says the pattern is real, recurring, influenced by forces we partly understand, possibly affected by climate change in ways we are still working out and capable of returning. The same science gives no support to the idea that a repeat of the 1918 death toll is looming, because that toll depended on a specific and largely vanished set of circumstances. To be watchful is justified, to be frightened of a repeat is not. That leaves a constructive question, and it is the one that actually drives the scientists doing this work. If we are not bracing for a rerun of 1918, why study the connection between this weather pattern and disease at all? The answer is that the link between climate and health is real, general, and increasingly important, and that understanding old events like this one helps us prepare for the genuine, if different, challenges ahead. That is the reason this research matters now, and it is worth setting out clearly. If a repeat of 1918 is not what scientists fear, then it is fair to ask why they spend effort connecting a century-old weather pattern to disease at all. The answer is that the link between climate and human health is real, broad, and growing more relevant, and that careful study of past events teaches us how that link works. The 1918 story is valuable not as a prophecy of doom, but as a clear, well-documented case of climate and disease intersecting, the kind of case we can learn from. The general principle the study illustrates is straightforward. Climate and weather shape the conditions in which diseases spread, and they do so through ordinary, understandable mechanisms. They affect where people gather and how closely. They affect the health and resilience of populations through food, water, and exposure. They affect where the animals that carry diseases live and move. None of this is unique to influenza or to 1918. It is a general truth about how the physical environment and human health are tied together, and the war years are simply an unusually stark and well-measured example of it. One of the researchers put the broad lesson plainly, noting that these atmospheric reorganizations happen and they affect people, changing how we move, how much water is available, and what animals are around. That is the heart of it. A shift in the great patterns of the atmosphere is not just a matter of whether you need an umbrella. It can reshape the basic conditions of life across a region, and those conditions feed directly into health and disease. Understanding that connection is part of understanding our own vulnerability. This matters more now because climate research has become an increasingly essential part of studying disease. As the climate shifts, the maps of where diseases live and spread are shifting too. Illnesses carried by mosquitoes like malaria and the viruses behind dengue and Zika are sensitive to temperature and rainfall, and warming can expand or move the areas where their carriers thrive. Diseases tied to water, to heat, and to the movement of animals all respond to a changing climate. The discipline that connects these dots sitting between climate science and public health has grown precisely because the connections are becoming more consequential. The 1918 study contributes to that effort in a specific way. It shows that the connection between climate and a major disease event can be measured, dated, and cross-checked, rather than just asserted. By pulling a physical record from the ice, lining it up against independent weather and death records, and tracing the mechanisms, the researchers demonstrated a method for studying how climate shapes disease in the real world. That method, more than any single conclusion about ducks or trenches, is part of the lasting value. It is a worked example of how to ask these questions rigorously. There is also a humbler benefit, which is simply better history. For a long time, the 1918 pandemic and the misery of the First World War were understood mostly in human and political terms, with the weather as a vague backdrop of mud and cold. This work puts a measured physical force into that history, showing that an unusual climate did not just set the scene but actively shaped the death toll. Understanding the past more completely is worthwhile on its own, and it also sharpens our sense of how many forces combine to produce a disaster, which is a lesson with obvious modern use. So the reason to study this is not to frighten anyone about the next stuck winter. It is to understand, clearly and concretely, how the atmosphere and human health are linked, so that we can recognise and prepare for the real challenges a changing climate brings, which will mostly look different from 1918. The value is in the understanding, not in any prediction of repeat catastrophe. That brings us to the most important correction this whole report can offer, which is to measure honestly how much real risk the pattern carries today and to put the alarm of the title in its proper place. It is time to be direct about the size of the real risk, because a story like this can easily leave a heavier impression than the evidence warrants. So here is the plain accounting. The weather pattern behind 1918 is real, it recurs, and it can return in some form. The catastrophe that accompanied it last time depended on a specific combination of circumstances that no longer holds. The honest conclusion is that the pattern deserves scientific attention, and that a repeat of 50 million deaths from such a pattern is not something the evidence points to. Start with what is solidly true, because the foundation is genuine. An unusual, persistent atmospheric pattern did settle over Europe for 6 years a century ago. It did flood the continent with cold, wet marine air. It did contribute directly to deaths through exposure, infection, and hunger, and it did help a new influenza virus spread and kill on a massive scale by crowding and weakening an already strained population. The ice core records it, and independent temperature, rainfall, and mortality data confirm it. None of that is exaggerated. It is careful, cross-checked science, and it should be taken seriously. Now hold that against what would be required for a similar death toll today, because this is where the title's alarm meets reality. The 50 million did not come from weather alone. It came from weather landing on a continent at total war, with food supplies collapsing, with no antibiotics, no flu vaccines, no modern intensive care, no rapid communication, and no coordinated public health response, just as a dangerous new virus emerged. Every one of those aggravating factors is different now in much of the world. The weather pattern was one necessary ingredient in a recipe that had many, and most of the others are absent today. This is the crucial correction to the feeling the title invites. The phrasing suggests that if the atmosphere behaves a certain way, mass death follows, as if the sky alone holds the trigger. The evidence says something quite different. The sky supplied conditions, and those conditions turned lethal only because of a world uniquely unable to withstand them. Change the world, as the last 100 years have, and the same sky produces a hard season rather than a demographic catastrophe. The recent cold winters that followed exactly this pattern are the proof. Disruptive but survivable. Nothing like 1918. That does not mean the modern world is invulnerable, and false comfort would be its own kind of dishonesty. Climate and health are truly linked. Persistent weather patterns can still cause real harm, especially to the most exposed and the least protected, and new diseases will continue to emerge. There are genuine risks in the relationship between a changing climate and human health, and they deserve serious, sustained work. But those real risks look different from 1918, and they are best met with preparation and understanding, not with fear of a specific historical disaster repeating in the same form. The right posture, then, is calm vigilance, and it is worth naming what that means in practice. It means scientists keep watching the North Atlantic patterns, keep improving forecasts, and keep studying how climate shapes disease, all of which is already happening. It means public health systems stay ready for new outbreaks, whatever their trigger. It means individuals do the ordinary sensible things that protect against respiratory illness in cold seasons, the same plain measures public health authorities have long advised. None of it requires alarm. All of it is the steady, unglamorous work of being prepared. So the size of the real risk is this. The weather pattern is a real and recurring feature of our climate, worthy of study and attention. The catastrophe it accompanied was a product of its time, dependent on conditions we have largely moved beyond. Watchfulness is wise. Dread is not warranted. That balanced conclusion is what the evidence actually supports, and it is the honest answer to the question the title raises, which leaves only the last task to return to the ice itself, to sum up plainly what it has told us and what it has not, and to point to what comes next. We began at a saddle of old ice high in the Alps, and it is fitting to end there, because that quiet column of frozen water is what made this whole story possible. Drilled from the Colle Gnifetti glacier and read with care, it preserved a clear record of 6 years when the air over Europe behaved unusually, from 1914 through 1919. That record, published in the autumn of 2020, is the thread that ties together a war, a pandemic, and the sky above them both. The ice remembered what the living had largely forgotten. What the ice tells us, with real confidence, is now clear. For 6 years, a stuck atmospheric pattern over the North Atlantic flooded Europe with cold, salty marine air, the strongest such episode in a century. That weather killed directly through cold, rain, exposure and hunger, raising deaths in step with its surges, and it helped turn a new influenza virus into history's deadliest single pandemic, not by carrying the disease, but by crowding and weakening a population already worn down by war. The evidence for this comes not from the ice alone, but from temperature, rainfall and mortality records that independently agree. That much is solid ground. What remains uncertain is just as important to say plainly, because honesty about the edges is what makes the solid centre trustworthy. We do not know the exact cause that locked the pattern in place for so long, only the kinds of forces that shift the system. The idea that disrupted duck migration helped the virus jump from animals to people is a reasonable hypothesis, not a proven fact. The precise death toll is an estimate, at least 50 million and possibly higher, known well enough to be sure it was immense but not to the last million. And how climate change will affect such patterns in the future is an open question that scientists are still working through. These are not flaws in the story, they are its honest limits. The most important thing to carry away is the correction to the fear the subject naturally invites. The pattern behind 1918 recurs, and a version of it will return, because it is a normal mode of the Atlantic atmosphere. But the catastrophe was the product of that weather meeting a world at war, starving and without modern medicine, just as a deadly virus emerged. That combination, not the weather alone, produced the 50 million. The world has changed enormously since then, and the same pattern today brings a difficult season, not a demographic disaster. Watchfulness is earned. Dread is not. As for what to watch next, the answer is steady and unspectacular, which is exactly how it should be. Scientists continue to monitor the North Atlantic patterns, the wandering Iceland low, the blocking highs, the negative swings of the oscillation, and the strange cold blob in the ocean, using instruments far finer than any single ice core. They continue to study how climate and disease connect, knowing the real challenges ahead will mostly look different from 1918, and more cores will come out of more glaciers, each one another page of the planet's own record, read carefully, cross-checked honestly, and added to what we know. That is the calm and accurate place to leave this. A glacier kept a receipt for 100 years, and when scientists finally read it, it explained a piece of one of the darkest stretches in human history, clearly and without drama. The lesson is not that the sky is poised to kill us, but that the atmosphere, the ocean, and human health are bound together in ways we're still learning to measure. Understanding those ties patiently and honestly is how we stay ready for whatever the climate does next. We will keep reading the ice, and we will keep these reports coming.